chair. I have Earl Bellinger, Natarajan, and Antonio Porras. And first, if you wouldn't mind explaining a little bit about who you are and what you do. So, maybe Antonio first.
Yeah, I'm a Heisen-Simons postdoctoral fellow here at Yale in the astronomy department, and I work on black hole formation and galaxy formation theory.
I'm Natarajan. I'm faculty in the Department of Astronomy and Physics. I also happen to be the chair of the department right now. And also I'm the director of Yale's flagship interdisciplinary program called the Franke Program in Science and Humanities. So my research interests vis-a-vis black holes are that I'm very interested in understanding how they form, how they grow, how they evolve, and what are the multiple ways in which we can actually see them indirectly.
Hello everyone, my name is Earl Bellinger. I'm an assistant professor here in the Department of Astronomy. I'm also part of the Yale Foundation for Data Science Institute, and my research mostly lives at the intersection of artificial intelligence and stellar astrophysics, and particularly pulsating stars. And I'm interested in a couple aspects of black holes. First of all, stars are the progenitors of at least stellar mass black holes, but also stars are probes, potential probes of dark matter, of which black holes might be a solution to the dark matter problem, and these pulsating stars might be sensitive to them if they are.
Thank you. So we're going to go with the most basic question here, which is, what is a black hole? And maybe it's not so basic, because it's very mysterious, and that's why our theme is centered around black hole growth. So how would you explain a black hole to the public? Let's start with Priya.
So I think one of the exciting things about black holes is that there are multiple ways to understand what a black hole is. And depending on the scientific community that you come from, the picture that you have to play with to understand what was totally different. So for physicists, a black hole is a place. It's a place where space is extremely curved and has very, very peculiar properties inside of a sort of a ring that is referred to as the event horizon, and encased in sort of extremely distorted space inside this horizon is likely a singularity, a place where we believe all laws of physics that we know about actually break down. They're no longer valid. So for physicists, black holes really are sort of the limit, they are sort of a way of thinking about the limits of our knowledge. They really push the limits of our knowledge. But when you think about astronomers and what they really think about as black holes, because we go out and try to find them indirectly, find evidence for them, there are three different ways in which we think about black holes. One is, as Earl just mentioned, they are stellar corpses. They're sort of the end state, so very massive stars. So if your natal birth mass of a star is 8 to 10 times the mass of our sun or above, then you live a glamorous life, live fast, die young, and leave behind a black hole as a corpse, right? So that, we believe, is the origin that's very well established theoretically. So there's enormously compelling and strong, almost incontrovertible, I would say at this point, evidence for the life cycle of stars, and therefore for the formation of those black holes. The other way to think about a black hole is to focus on its peculiar properties. They're like very enigmatic objects in the universe. One of the most enigmatic things about them is that the escape velocity, their gravity is so intense that the escape velocity from their surface is incredibly high, and it's actually the speed of light. So to get a sense of what the escape velocity is, if you take the surface of the Earth and you see these launches of rockets, the reason we need booster fuel is because they have to be accelerated, and there's a velocity, they have to have an escape velocity of 11.2 kilometers per second is what you need to free yourself of the grip of gravity of the Earth, to go beyond, right? So if you think about that in terms of escape velocity, then the escape velocity from a black hole, like if you just kind of bend your mind around and say, okay, if I can think of a black hole as a place, as like an Earth, like an object, the escape velocity is the speed of light. And that's the reason we say not even light can escape a black hole. And of course, that region that we're referring to is that event horizon. The third way that astronomers really think about a black hole is a very compact mass, a lot of matter that has been compacted into a very tiny size. And when I talk about the size of a black hole, it's really the event horizon that one is talking about. And the size of this event horizon is proportional to the amount of matter that there is in there. It's very, very tightly packed. So these are sort of different ways to think about a black hole. And when I said the physicists are thinking about them as real distortion divots in space-time, that kind of all of this ties to Einstein's theory of general relativity, where the entire universe is a four-dimensional sheet, and all matter creates little potholes in this space-time kind of fabric, and the black hole there causes a puncture. So here you have like fodder for thinking, playing around with these multiple definitions. Yeah.
So Antonio, do you think of this in terms of a more physical process, and if so, how does that work in your mind?
Yeah, I guess when Priya was describing the 3 stages, I thought of they could also be thought as an evolutionary stage. So you could start after your glamorous life, your star is dead, but a new object has been born, and you could start from that new object to become very massively tight object called supermassive black hole, and that's the stage where I focus the most, is understanding this very massive black holes that are in the center of galaxies, which are collections of stars, gas and dust and planets, and they are supposedly close to the center of these galaxies, but not necessarily have to be. And then I like to think about how these black holes came to be, and I like to think about galaxies and black holes as having a very close relationship with one another, and galaxies as people, because galaxies live in different neighborhoods where you may interact with more galaxies than others, and we all live in different neighborhoods. We grow up in different places. And so I like to think of the history of a black hole and the galaxy, which could be very well connected, depends on the parameters where it started, and the neighborhood, and how many interactions have had, and how lonely it's been, and for how long that throughout that history the black hole and galaxy have been.
That's awesome. That's a great concept to visualize. So Earl, can you move us more towards black hole growth and how you think black holes grow? Like, what are the options for that?
Yeah, definitely. Well, okay, I should begin by saying that, we have like literally the world's expert beside us, so it's certainly a better person to field this question, but maybe I can get the ball rolling. So one thing that I find helpful is that we can distinguish 4 different categories of black holes based off of their mass. So there are supermassive black holes. There's a supermassive black hole living at the center of the Milky Way galaxy. There's probably supermassive black holes at the center of every galaxy. And in some, there's more than one. There might be 2 supermassive black holes merging with each other, for example. So these have millions or billions of times the mass of the sun, perhaps even more. And one of Priya's influential papers is how large can such a black hole actually even get, which is, I think, one really interesting foundational question. Okay, so those are the supermassive black holes. There are less massive black holes that we call intermediate mass black holes. These might be thousands of times the mass of the sun. The evidence for supermassive black holes is extremely compelling. In fact, we have some direct images now. The evidence for intermediate mass black holes is more tenuous. There's candidates, but it's that they're much more difficult to find. Then we go to even lower mass. We get to stellar mass black holes. When a massive star dies, it leaves behind a black hole that's maybe something like 10 times the mass of the sun. And these things are everywhere. Our Milky Way galaxy probably has around 100 million such stellar mass black holes. So they're just part of our galaxy. And we are finding them now in large numbers. For example, when they merge, they create gravitational radiation. And so we have examples of these stellar mass black holes merging. We've also found them as the invisible companions to stars using astrometry. So we're looking at the positions of stars in the sky. Sometimes you see a star orbiting an invisible object, and we can work out the mass of that object, and it turns out to be a black hole. And then the fourth category is if we go yet lower mass, and this is the most speculative of them all. It's an idea going back to Stephen Hawking, who suggested that in the immediate aftermath of the Big Bang, you could have had direct collapse of very low mass objects. These are so-called primordial black holes, primordial because they come in the immediate aftermath of the Big Bang. Some of these were created from the direct collision of radiation, which is kind of amazing to think about. We were talking about the escape velocity around such a black hole being the speed of light, so light can't escape. In this case, it's sort of like light itself collapsing into a black hole. And these black holes might have the mass of an asteroid if they exist. We do not know if the universe produced these things, but it's one of the holy grails of astronomy to try to find them. And so you get to the question of black hole growth. Well, we have these 4 different categories based on their masses. And so the question is how do you actually grow a black hole? So there's a few ways. The main ways are, like I mentioned, mergers. If you combine 2 black holes together, then you can produce a black hole of even larger mass. There's also accretion. So matter can, matter is attracted to a black hole gravitationally. It can kind of swarm around it and create an accretion disk, and then the black hole can feed on that disk to grow even larger. And then the most speculative way to grow a black hole is that if indeed these very tiny primordial black holes exist, then every so often they'll find their way inside of a star, and then they'll eat it from the inside out, and they'll grow up to a black hole of the mass of that star.
Thank you. So Priya, why do we care about black hole growth? Like, how does it impact us and what we know about the physical world?
Yeah, so it used to be, right, so the black holes started first before they became real. They were actually a solution to one of Einstein's equations. So the equations of general relativity, there are about 10 equations, coupled equations. And he himself thought there probably wouldn't be any solutions to it even, because it's so complex. But then it turns out that Carl Schwarzschild, who heard Einstein's lectures on his theory of general relativity, was at the front, World War I, in the trenches, and he heard that lecture, got the notes, and he actually found a solution. And the solution was, and what we mean by a solution is the shape of space around a really concentrated mass. Because as I told you, that mass causes a puncture in the fabric of space-time. So they were believed to be like this odd mathematical solution, not corresponding to anything real in the universe for a very long time. Till the 1930s, when the theories of stellar structure and evolution, people started to show, Chandrasekhar and others were able to show that these are an inevitable consequence of this end state of stars, that you would form a black hole. That's when they sort of became real. But they still, and then people started finding these supermassive black holes in the centers of galaxies and so on. But they were, it took a while for them to start being considered kind of important in terms of shaping the universe. So they were thought to be, okay, they are sort of, a consequence of this formation of structure. They kind of end up and sit in the center of a galaxy. What do? They were supposed to be bit players in the cosmic drama, right? And then over the years, and especially over the last 20 years, they play a starring role now in the formation of all visible matter, it turns out. So they really shape how many stars form in a galaxy. So they modulate that, and because they can, they take in matter, they put out jets, or some matter that doesn't go in, gets expelled with magnetic fields as jets. So, and they have a reach that is way beyond their size, which is very compact in a galaxy. So black holes can fire up these jets that actually punch through and go well beyond a galaxy. And so that's how they modulate, they heat as they go along. And so to form stars, you need to cool gas and make gas denser. And so we believe now that they're like the thermostats that really control when you form stars, when you shut off forming stars, because if you heat, you shut off star formation by preventing cooling. And so they are now really important in our story, and it can be argued that we wouldn't be here if there were no black holes. It's because the galaxies would not have formed and be stable and be in the way they are. So, poetically, I think one could argue that we are here because the Milky Way has a central black hole where it does. Like we're sort of in a sweet spot, right? We're not too close, so we are not impacted by the gravity of that black hole at all. But all the drama that it sort of created has kind of enabled the formation, most likely, of not just our star, but the solar system and life and so on.
Thank you. So, Antonio, how do scientists know that black holes or black hole growth exists, and how can you observe black hole growth? Can it be perceived by any of our senses?
So the most direct way is through X-ray telescopes, which are in space, and you can detect the photons from the source of where the gas falls close to the event horizon, or within some scale. It emits some radiation, and that radiation is what is captured by the X-ray telescopes. So that's one way of knowing whether there's a black hole that is actively accreting. The other thing.
So does that mean that the X-ray radiation escapes the escape velocity?
Yeah, but definitely it is something that
horizon?
is close. It's close enough to the black hole, but it's not past the event horizon. So it's not. It escapes the escape velocity. Yeah.
And is that what the jets are?
Yeah, so that's something that where the black holes. But the jets themselves are the outflows, so not necessarily being accreted into the black hole, so the black hole has grown. It is unclear if that jet is a result of an over-abundant black hole that loves to eat so much that it just throws up, and that throw up is the jet. I don't know, it sounds weird, but I think about it like that. and so it could be an aftermath of if a black hole eats so much that it cannot take any more material.
Right. Yeah, no, and just to quickly add, right, so all of this phenomena that we see, as Antonio pointed out, are happening well outside the event horizon, like hundreds of times. That's why we're seeing it. So all this evidence, nothing has broken that sacred boundary yet. Everything that we see is happening well outside.
So I had one more question for Earl. You talked about these 4 different classifications of black holes based on mass. Is there a thought that the smallest is first and the biggest is last, or vice versa, or are they considered independent?
These primordial black holes, they could actually span any scale of mass, and so one possibility is that a small number of supermassive black holes also spawned at the beginning of time, but we don't expect that to be the origin of all supermassive black holes. And in fact, if these primordial black holes exist, probably they peak at very low mass. And so if they exist, that would be the first category of black hole that was created, because this would be very soon after the Big Bang, within perhaps minutes, maybe even within seconds. And then you touch on a very interesting point, again, where Priya is literally the world's expert, which is how can you make a black hole that is so supermassive if you're using astrophysical processes, not spawning it right after the Big Bang. And so you get to this question of how fast can a black hole actually grow? And so we have kind of speed limits astrophysically to how fast a black hole can grow. If you think about packing matter into a sphere, symmetrically, there's only so much you can pack in before you kind of blow away the stuff that you're trying to pack in, and that sets a limit on how fast you can kind of cram matter into a collapsed object. And if you do the math, you find that over the history of the universe, it's very challenging to grow something at that rate, even if you continuously grow something at that rate. If you start from the mass of a stellar mass black hole, which could have formed within a few 100 million years after the Big Bang, the massive star dies and creates a black hole, and then you just continuously feed it to try to make it supermassive. you have a challenge to make such a black hole in the history of the universe, and this problem is exacerbated because recently there's evidence of these black holes, supermassive black holes, existing very early on in the universe. So how do you make them not just be so massive today, but so massive early on? And again, this is Priya's line of research, so you might want to ask her.
So I have two more questions for Priya. We talked about mergers and accretion and the star eating itself up and primordial stars. So are these all three possible at the same time, or do scientists think that there is only one of them and they're trying to pursue which one of them they are?
So I think the way to think about black holes is like as a population, like there, and depending on what is available, they are sort of predatory, and so whatever is available near them. So if you have a black hole that is sitting in a very gas-rich galaxy, in the center of a very gas-rich galaxy, with a nice, well-formed accretion disk that is feeding it, then it will feed gas and grow by accretion. And when it does that, it's actually feasting, and you would see all the matter. So the reason you see all these X-ray glows is you can imagine what's happening is that these accretion disks are extending well outside the horizon. So we are way, way outside, thousands, hundreds of thousands of times the event horizon. They extend out to them. But the gas gets pulled in from the disk, and as it's getting pulled in, it gets sped up and heated up. And it's that glowing gas that glows in the X-rays that we see, right? So it's like the dying gasps of the gas before it crosses into the event horizon. So these processes can happen simultaneously. They tend to happen, like this sort of steady feeding by an accretion disk is something we believe the most normal way in which most black holes grow for the majority of their life. However, in the very early universe and in the very late universe, there are particular cosmic contexts in which the crashing into each other. A very early universe is very dense, so you're quite likely to kind of crash into each other. The probability is much higher. So at that stage, and remember, this is all happening in the backdrop of an expanding universe that's not only expanding, but it's an accelerated expansion. So it gets harder and harder for two things to crash into each other as time goes on, to closer to us. The age of the universe is 13.8 billion years. So as you get closer and closer to today, the universe is getting less dense and less sparse. The probability to find another black hole to collide with in another galaxy is low. But there's a particular context where you have a very dense patch of the universe, and there those collisions can happen. So there are times where each of these ways of growing, so we think that they don't all simultaneously happen, but they have all happened, for example, in the lifetime of a black hole. So for example, the black hole in the center of the Milky Way probably grew from a tiny seed, probably grew a lot by accretion, had a few mergers here and there, then accreted, had a few mergers, and so on. So we think that you can map out, and that's the sort of work that Antonio does, mapping out how the black hole could have grown and by which process it could have grown over time.
Thank you. So I want to give us time to actually do our art, but do any of you have any questions for the panel?
As the mass of the black hole is increasing, how is the event horizon changing?
It's also increasing. It's linearly proportional, directly linearly proportional. That's a great question. Yeah. So one way to think about how black holes are growing visually is just to think of the event horizon. So think of it in 2D as a ring. You can think of the ring kind of expanding. And you can also imagine, like, one of the things that I often find kind of exciting to think about, right? When thinking about accretion, you can think of this ring kind of wobbling, right? It's kind of feeding and it's kind of changing. So yeah, it's directly proportional.
Other questions? Yes.
I'm just puzzling about the event horizon and the speed of light. If there's growth in the size of the black hole, is it effectively moving faster than the speed of light?
No.
No.
Why do you?
I'm just trying to think through.
No, so I think the way we think about it, as I said, right, reconciling this sort of astrophysical picture of feeding matter in and the puncture of space-time, there are sort of small gaps in how we connect those views. So basically the event horizon is proportional to the mass of the black hole, and when mass crosses the event horizon, we assume that it goes into the black hole because it's a point of no return. And we just add that to the reservoir of mass that we refer to as a black hole. And because it's gone up, it means the corresponding event horizon now has become a little bit bigger.
I would like to add 2 points. So one point is, even though they are called black holes, we can sometimes see the black hole, but what we're seeing is the light emitted from the radiation before the light goes into the event horizon, which is what Priya was discussing. So, but that doesn't mean that the speed of light is faster because we're able to see that light. It means that that light was way farther from the event horizon before falling in there. And I forgot the second question. The second part is that a lot of times in the internet we see pictures, two-dimensional pictures of black holes. I would challenge you to think about a three-dimensional picture of a black hole.
Or even four. I mean, in truth, they live in a four-dimensional universe, right? And that's pretty hard, right? It's the tesseract, those of you who've seen.
Yeah, that's right, because that is our task, right? Is
Yeah,
to,
it's like-
to visualize the growth, and so that really means thinking four-dimensionally about a black
Yeah,
hole.
I mean, if you want to. You can also do something clever in lower dimensions, but, you know. Interstellar had some nice visualizations, right, of Gargantua as well as falling through the tesseract, which is four-dimensional.
Well, thank you very much. And let's everybody give a round of applause for our panelists.
Thank you.